Hey students, welcome to lesson 6-8. In today's lesson we will be transforming polynomial functions. So we spent a pretty good portion of the course so far talking about different kinds of transformations of functions. We started off looking at transforming linear functions. We also looked at transforming absolute value functions and even quadratic functions. So in today's lesson, we're going to be looking at transformations on the whole group of polynomial functions. And so we're going to primarily be focusing on vertical translation, horizontal translation, vertical stretches and compressions, and also on the reflections over both of the axes. And in some cases, due to the complexity of some of the functions that result, some of the rules or equations we will leave unsimplified. So that's basically what these two learning goals state. So let's do a quick review of the transformation rules. So first of all, the most basic and probably the easiest one to apply is a vertical translation. So remember, in a vertical translation, basically we're taking some kind of function and we're sliding it up or down. And so to apply a vertical translation, all we have to do is just take the function f of x, whatever that equation might be to start, and we just add some k, some constant value, on to the function, and that will have the effect of sliding it up or down. So if we're going to take this example here, f of x is equal to 4x squared minus 8x. If I wanted to slide it down 3, I would basically take this function, 4x squared minus 8x, and I would subtract 3 from it. And that would result in the function 4x squared minus 8x minus 3. So that would be the transformation of the original function down 3 units. Now, if instead I wanted to do a horizontal translation, in the horizontal translations, we basically will go wherever there's an x in the polynomial function, and we'll take it out and we replace it with x minus h, where h is that horizontal slide amount. So basically we just replace x with x minus h. So if we use the same example, 4x squared minus 8x, wherever we see that x, we're just going to take it out, and we're going to put in place of it x minus whatever the slide amount is. Well, in this case, if we wanted to go right 3 to the right is a positive 3, so we'd be subtracting a positive 3. So that would actually stay an x minus 3. And so all I do is wherever I see an x in both places, I just replace it with x minus 3. So the difference here is that instead of x, we have this x minus 3. Now, if we wanted to expand that out and simplify that down, we could do that. But we're going to just go ahead and leave these, when we do horizontal translations, unsimplified, because as you'll see when we get to some of these higher degree polynomial functions, they'll be quite difficult to simplify. And so we're going to just be okay with leaving it in this form, and so we'll go ahead and say this is the transformation 3 units right of that function. Now, although we've studied both vertical and horizontal stretches and compressions, we've chosen just to focus really on the vertical stretch and compression. And you may remember those. The rule looks like this. Whatever the slide amount is, we call it A. Or I'm sorry, the stretch or compression amount is, we call it A. And so we apply a vertical stretch or compression by simply multiplying the function by A, whatever the vertical stretch or compression amount is. So let's say we want to go over here and do this example. We want to do a vertical compression by a half. So what we would do is we would take this half and we'd multiply the whole function that we want to transform by that half. So this is what that would look like, 1/2 times 4x squared minus 8x. And then we could go ahead and simplify that just by simply distributing that half through to both parts of that. And that would turn out to be 2x squared minus 4x. Now we'll also be looking at reflections, and we'll actually look at reflections over both the x-axis and the y-axis. And you'll actually see the rules here for both. This first one, which says to take the opposite of f of x, is a reflection over the x-axis. So you probably remember when we studied quadratics, if the leading term was negative, it was a parabola that was reflected over the x-axis. Well, basically, if you were to take the opposite of an entire function, polynomial function, it would just essentially reflect that function or that graph over the x-axis. Now that second one listed, which says replace x with the opposite of x, is actually a reflection over the y-axis. So if I wanted to reflect some kind of function over the y-axis, I would simply go in and wherever I see x, I would replace that x with a negative x, or the opposite of x. So let's take a look at each one of these with this function that we're working with. Looking first at a reflection over the x-axis, which means we want to use the rule, take the opposite of f of x. And basically what that means is we're going to take the opposite of this whole thing, 4x squared minus 8x. And if we were to distribute that negative through, then that would give us negative 4x squared plus 8x. And that would be the equation for a reflection of the original over the x-axis. So let's say I wanted to go over the y-axis. So then I would want to use this rule, f of opposite of x. In other words, take out the x wherever you see it in the function and replace it with the opposite of x. So what I'm going to do here is I'm going to take this function, this 4x squared minus 8x, and wherever I see that x, I'm going to replace it with the opposite of x. So that occurs there in the 4x squared part is now 4 times the opposite of x squared, and then minus 8 times, and then again I'm replacing x with the opposite of x. And so if I were to simplify that, basically that negative here that's being squared, if you square a negative, remember it turns it into a positive. So it has no effect at all on this first term. It keeps it a 4x squared. But on the second term, that negative x multiplied by a negative 8 makes it a positive 8x. And so this equation, if you were to graph it, would show a function that is reflected over the y-axis. Now, one way to kind of verify that is to go ahead and graph the original function and your transformed equation on the same set of axes on the graphing calculator, and then just compare the results and see if, in fact, that kind of movement happened to the graph. Did it reflect it over the y-axis? Did it reflect it over the x? Did it slide it up 3 or down 3 or whatever? And so that is something that we're going to be exploring in this lesson, is how we can use the graphs to just verify our findings. And we'll do this as we look at this first example. So example A says, for f of x is equal to x cubed minus 6, write the rule for the function g of x after the given transformation, and then sketch its graph. Use your graphing calculator to see the shape of the graphs for your sketch. And so the question asks me to transform it by sliding it 2 units down. So what that means is I'm going to use this rule right up here. I'm going to use the rule for a vertical translation. And basically it just says take the function, well this is my original function, x cubed minus 6, and I'm going to just subtract 2 from it because it wants me to go 2 down, so I'm going to subtract 2, which now when I simplify it, I can go ahead and add the like terms, add the minus 6 and the minus 2, which makes, oops, I'm sorry, that was supposed to be an x cubed. It's an x cubed, which would give us x cubed minus 8. Now here's what that would look like in the graphing calculator. So looking at this original graph here, highlighted in orange, this is the original x cubed minus 6, and then we slid it down by subtracting 2. We slid it down 2, and then that turned out to be right here, and that's at x cubed minus 8. And so we can clearly see that the one graph, the original graph, if you just count down 2, there's a corresponding point on the new graph, x cubed minus 8. Okay, so let's go ahead and take a look at another one. Okay, so in this next example, we're going to use the same original function, and we're going to transform it by moving it a certain amount, and we can see it's actually graphed here. So we're going to see if we can figure out what's happened, what transformation has occurred to take this blue graph and move it to the position of the red graph. Well, you can see here that basically what's going on is it's sliding to the left. And if we picked a certain point, say maybe this point right here, and we look to see how many units did it move it to the left, it looks like it's moved 1, 2, and 3. So this looks like it's a transformation, it's a translation left 3. So if I want to go ahead and write the rule for that, remember that it's a horizontal slide, which means we have to apply this rule right here, which says replace the x with x minus h, where h is the slide amount. So if we were to take a look at this function, x cubed minus 6, we would just take out that x and we replace it with x minus negative 3. Well, left 3 is a negative, right? So x minus negative 3 would turn out to be x plus 3. And that's why we say x lies to, because that looks kind of a little bit counterintuitive. And so if we wanted to simplify this, it would be pretty complicated, because we have this x plus 3 is actually cubed, so we'd have to do that binomial expansion using maybe Pascal's triangle or whatever. And so I think in each of these cases, we're just going to leave them unsimplified for horizontal translations. So when you have something like this, it's okay to just leave it in this form. And actually then it's clearer in the equation even, the fact that this was a horizontal slide, because you can see that x being replaced by x minus whatever the slide amount is. So let's go ahead and turn the page. Okay, so we've got one for you to try here. We're going to make C the you try question. And so keeping in mind that the original graph, which you can see on mine is the blue one, so it's the one that's labeled F right here. And if that one's the original and it is x cubed plus 4, then see if you can write a rule for g of x, which is for the red graph here. So we want to know what would be the transformation, what's happening here, describe it, what type and how much, and then write a rule. So go ahead and pause the video now and try example C. Okay, so that one was clearly a translation down, and if you just counted the little tick marks, it looks like it was slid down 5 units. So then I went ahead and applied that rule by taking the original function and just subtracting 5 from it, which turned out to give us a final equation of g of x is equal to x cubed minus 1. Okay, so in this next example, we're taking a look again at x cubed plus 4, and we want to write a rule for a transformation of this function 2 units to the left, and we're going to want to graph this. So what I'd like to do is just go ahead and first look at f of x, and we'll graph that first. And so to graph that, let's just go ahead and I made a little table, a little t-chart, and I'm just going to pick some numbers around the origin to substitute in so we can get an idea of what this graph looks like to begin with. So if I were to take a negative 2 and substitute it into x cubed, negative 2 multiplied by itself 3 times is a negative 8. So if we add 4, that would make it a negative 4. If we substituted a negative 1 in, negative 1 cubed is negative 1 plus 4 is 3. And if we substituted a 0 in for x and cubed it and added 4, we'd have 4. Put a 1 in and cube it. Well, 1 cubed is 1. Add 4, that's 5. And then if we cubed 2, we'd get 8, and we'd add 4, which is 12. So let's see which ones of these we can actually fit on our graph. So negative 2, negative 4, that would fit on our graph right here. Negative 1, 3, so there's negative 1, and up here at 3. At 0 and 4, so that's right here. At 1 and 5, we can fit that on there, and that's about it. So basically what's happening with this graph, and if we connect it, it's kind of just that typical cubic graph. It's kind of curving through there, and it's continuing on up. In fact, at 2, the next point would be 2, 12, and so on. So it's going to continue going up And it looks like that. So that's our original graph. So if we wanted to translate this 2 units to the left, the rule is to substitute in or replace x with x minus whatever the slide amount. Well, left 2 would be subtracting -2 because left is considered to be negative. And so if we were to place x with x minus -2 into that original function, and we went ahead and simplified that minus negative into a plus, it would turn out to be x plus 2 cubed plus 4. And so the effect of that really is just going to be to move every one of these points 2 units to the left. So we could really just graph it by just taking each one of these points and moving 2 to the left. So like for instance, this one I could go 2 to the left, it would be right there. This one 2 to the left, it would be here. 2 to the left, and down here 2 to the left. And then if we were to just connect them with that same curve, and we could see that that's going to go up like that and run right along next to it, but just 2 units to the left. And you can clearly see that slide 2 units to the left all along the graph. Okay, so let's take a look at this next example. We're going to be focusing on reflections here. So we have this function x cubed plus 5x squared minus 8x plus 1. And it says write a function g that performs the transformation and then sketch its graph. Well, it turns out that this graph that's included in the notes is an incorrect graph. And so once we write this rule, I've graphed it on the graphing calculator, and I'll show you what these should look like. So anyway, we have this function. It's some kind of cubic function, and we want to reflect it across the x-axis. So remember, this is the rule for reflection across the x-axis. It says take the opposite of f of x. In other words, it says take the opposite of the entire function. And so basically what's going to happen is I'm going to take the opposite of x cubed plus 5x squared minus 8x plus 1, and that's going to essentially just change the sign on every single one of these terms and make it g of x is equal to negative x cubed minus 5x squared plus 8x minus 1. So by distributing that negative through, it changed the sign on everything, and this is what it would look like. So this is actually the original one. This is the graph of the original function here, and I did adjust the window to go up higher. I actually went up to positive 50 up here on the y-axis and down to negative 50. And that way I was able to see both the, that peak, that maximum value, relative maximum, relative minimum value, so you could get the true shape of the graph. So that's what the original looks like, and this is what the graph would look like after it was reflected over the x-axis. And there's the graph in the red, that is the reflection. And you can see in this table here that it does show those 2 functions listed in the y equals menu. And so you can see that basically by just changing the sign on every one of those terms, you're going to get that graph to flip over the x-axis. Okay, so how about a reflection over the y-axis? So this time we have the function x to the 4th minus 8x squared plus 1, and it's graphed here. And again, the window has been adjusted somewhat to ensure that you could see the lower region of the graph. And basically what I did to adjust the window is I went up to 25 on the y-axis, down to negative 25, and then I only went out to minus 5 on the x and positive 5 on the x as well. And that way it just gives you a little better idea of what this graph looks like, because if you didn't adjust the window from a standard window, you wouldn't even see these little dips in the graph where they come down and have those relative minimum values and come back up. So you wouldn't see that W shape of the graph. So let's take a look at what the rule is. The rule to do this reflection across the y-axis, which is what I want to do here, I know that rule is this, f of the opposite of x, which means I'm going to take out the x anywhere I see it, and I'm going to replace it with the opposite of x. So basically right here in this function where I see x to the 4th, I'm going to replace that x with negative x, okay, and then where I see the x here, minus 8, and then I'm going to replace that with negative x, And now I'm going to simplify this. Well, if you were to take something positive or negative and raise it to the fourth power, you're always going to get a positive because you're multiplying an even number of either positive or negative things. In this case, an even number of negative things. And so that's going to turn out to be positive. This turns out to not change at all. It's still just x to the fourth. And the same thing is going to happen here with this negative x. If you square it, negative x times negative x would turn out to be positive x squared. So it does not change that at all. And so if you look at that and you compare it to the original, this is the exact same equation, which means it's going to be the exact same graph. And so if I were to, and that's because if you think about that graph, it's already symmetric about the y-axis. So if you were going to flip it across, the part that's on the left-hand side is going to go to the right-hand side and vice versa. And so not only is this the original graph, this is also the reflection over the y-axis. It's like you can see the original, and then you can see the new one just kind of mapping right up on top of the other one. It's just kind of turning around the y-axis and landing right back onto itself. Now, the reason why that occurred here, that the graph looked exactly like the original, is because all of these exponents turned out to be even exponents. And so they basically just canceled out the effect of that replacing the x with negative x. Let's go ahead and look at the next example. Let's turn the page. Okay, so in this example, we're going to be looking at compressing and stretching a polynomial function vertically. Again, we've just chosen to focus on only the vertical, so the rules that we'll be looking at for compressions and stretches will be just the vertical one, and that's a times f of x. So it says look at the graph f and g on the same coordinate plane. And so you can see that f is the blue one, that's the original one, and then the red one, g, is the compressed one. And, well, actually, I just kind of gave you a part of the answer then because I just said it's a compression because you can see how it was compressed or pushed back towards the x-axis. This is being compressed vertically. So that's what we have to find out is by how much. So we know it's a compression, so we could write as far as our description of the transformation is it's a compression vertically. But by how much? Well, it looks like, say for instance, we took this point right here that's at, right on, let's see if you can see that. I don't know if you can see that color. Make it a little darker right here, this point right there. And we compared it to its corresponding point on the red graph. It looks like it originally started off at 1, and the new point's now at about a half. And so it looks to me like this is a compression by a half. So that's what I'm going to guess. It's a vertical compression by a half. And that seems to really describe what's going on with the rest of the graph as well. It looks like in each case, each point is about half as far away from the x-axis as it was to begin with. So then this rule that I'm going to apply is I'm going to take a half and multiply the whole function by that a half. So my new function, g of x, is going to be found by taking 1/2 of 2x to the fourth minus 6x squared plus 1, and that's going to be x to the fourth. If I distribute that half through to each thing, it's going to be x to the fourth minus 3x squared plus 1/2. Okay, so our final learning goal is to look at combining transformation and write some rules that would describe multiple transformations of a polynomial function. Okay, so we're going to start off with this function, 6x to the fourth minus 3x squared. And in example A, we're going to do a vertical compression. So we're going to compress vertically by a factor of a third, and then shift 2 units to the right. So let's first of all take a look at the vertical compression. So that rule is going to be, we're going to take and use this rule, 1/3, because that's the compression factor, times f of x. And so basically every one of these pieces, each part, each term in the f of x is going to be multiplied by a third. And so what that's going to give me is a third times 6x to the fourth minus 3x squared, and that is 2x to the fourth minus x squared. But now that second transformation, we have to use this rule that says that's a slide left or right. In this case, it's a slide right. And so what the rule is to replace x with x minus h. So in this case, I'm going to replace x with x minus 2. Because right 2 is positive 2, so x minus positive 2 would be x minus 2. So now what we're going to do is right here, wherever we see an x, we're going to take it out and replace it with x minus 2. And the same thing here, where we see that x, it's going to be replaced with x minus 2. And although this could be simplified, we're going to choose not to simplify it because it would, again, involve quite an elaborate process to raise x minus 2 to the 4th power. I have to do that binomial expansion, and the same thing with x minus 2 squared, and then subtract them. So this is okay to just leave it unsimplified in this way. So that depicts the compression of a factor 1/3 followed by a shift or a slide 2 units to the right. And usually when we apply two different transformations, the first transformation we call it g of x, and the final one we usually call h of x. So that's what we're going to call our final function, is h of x. Okay, so how about another one? So this time we want to take that same function and reflect, so again we're going back to the original, this 6x to the 4th minus 3x squared. And we want to reflect it across the y-axis. And then we're going to shift it 2 units down. So the first part, this first one, reflect across the y-axis. This is what the rule is going to look like. So across the y-axis, it's f of opposite of x. In other words, we're going to replace x where we see it with the opposite of x. And so when we take that x out that's next to the 6, we'll put in negative x, raise it to the 4th. Same thing here with the x squared. We'll replace the x with negative x and square it. And so basically what's going to happen here is both of these exponents are even. And so they're just going to cancel the negatives out and give me back my original 6x to the 4th minus 3x squared. And that gives us that first transformation. But now the second transformation is a shift 2 units down. And so that rule looks like this. F of x, whatever the function is, we just add the k value on. And so that's the slide amount up or down. And so in this case, we're going to go 2 down. We're just going to take this whole function, this 6x to the 4th minus 3x squared. And from that, we're going to go ahead and subtract, because we're going down to 2. And then that would just leave us with 6x to the 4th minus 3x squared minus 2. And that's our final function, which we'll call h of x. So that's our h of x equals that. And let's go ahead and leave C as a you-try question. So they want you in example C to reflect the function across the x-axis and then move the x-intercept 4 units left. Well, moving the x-intercept 4 units left is just, if you're moving the x-intercept, you're moving the entire thing 4 units left. And so that's basically a slide 4 left. So pause the video now and reflect over the x-axis followed by a slide 4 units left. And again, with the slides horizontally, you do not have to simplify them. So pause the video now. Okay, so take a look at your answer and see how you did. G of x represents the reflection over the x-axis, so really just everything changed sign. And then to apply the slide 4 units left, I just had to replace x with x plus 4, which is really the same as x minus negative 4. And so I just took out the x's in both of those terms and replaced them with x plus 4. And again, there's no need to simplify these. That's a pretty elaborate process. So that is our final answer. H of x is equal to the opposite of 6 times the quantity x plus 4 to the 4th plus 3 times the quantity x plus 4 squared. And that is going to do it for our lesson today. So I will see you in class.